Hello everybody, my name is Fujita from Kobe University. Now I'm involved in the research center at the Engineering Research Institute. Today I'd like to talk about the history of surface velocimetry at Fujita Lab, my laboratory. Thank you for inviting me as a special lecture. This is the overview of my research on surface velocimetry. I started my research from about 1991 to about 20 years of research I have been involved in. And I'd like to introduce myself. I'm a graduate from Kobe University in 1977. And right now I have just retired from the Kobe University just last year. So during my research, I developed several surface velocimetry techniques, large-scale PIV or STIV, and recently we have developed aerial STIV and STIV or something like that. And just recently we have developed a deep learning technique into the space-time image velocimetry. So I'd like to talk about the history and some algorithms about the technique. And before that, I'd like to explain the origin of the particle image velocimetry, PIV. Everybody knows that this technique has been introduced in the world by Adrian particle image velocimetry technique, and the PIV is termed by him. But actually, the Kobe University's Professor Yano has developed before that, 1983. So this is the only remained images that he has presented in Japanese journal. So this is actually the first trial to apply PIV to the surface velocimetry. So at that time we call it correlation method. So please remember that PIV was firstly invented by Professor Yano, my professor. And this picture shows the measurement of flow at the right angle confluence in 1990, and this is come from the original idea of using space-time image expressions for searchlight. So at that time I was paying attention to the right angle confluence here. This is a large-scale separation bubble, and I set the searchlight here and observed the streamwise flow, velocity, and distribution with time. So in this case, we see that the quasi-periodic vortex shedding can be visually observed by making a kind of space-time image like this. Maybe this is the first time to express the surface phenomena as a kind of space-time image. This is the original idea. This idea was in my mind for a long time. And I have tried, after that I have tried the PIV to the aerial photographs in 1990 and 1990s. This is the photograph of the flood, 3.6 seconds apart, and I applied, this is actually a film, and I have applied this PIV by background image stabilization and obtained the surface velocity distribution very beautifully. You can see that there's a strong flow in the middle of the channel, and on the floodplain the velocity is decelerated. And after that this is maybe the first movie of which I have applied LSPIV in 1993 flood. Actually, this video was recorded on high-end videotape, and you see that this is a Yodo River flowing in Osaka. So this was given by my friend, and he asked me if these pictures can be used for the large-scale PIV. So I said yes, and I have applied the large-scale PIV to this one. So we get very beautiful streamwise velocity distribution from those images. And we have obtained the discharge more than 3,000 cubic meter per second can be measured first in 1990s. And after that, I will go to IIHR, Iowa Institute of Hydraulic Research. And this is my young age, me. And at that time, I worked with the staff, Marian Muste and Andrew Kruger. And I have published the Yodo River's case, and we have published the paper after that, 1998. And I left the Fortran code for the large-scale PIV and also PTV, and left it code free to use. So everybody who visited IIHR can use my software. So it has been widely used in the world right now. And after coming back to Japan, I applied large-scale PIV to various types of flow. This is the one example. This is a flow between groins. This is the main channel flow, and this is a recirculating flow in between the groins. And this is the actually pattern, and this is a very strong recirculating flow, and then they tend to decelerate afterwards. And this is another example that the Yodo River, this is the Uji River case. We have taken 3 shots from the tower, and this is a flow in the normal flow condition, and this is a case for the flood flow condition. So in this case, the normal flow condition had the mainstream will sometimes change to meanders, but in the flood condition they go just downstream straight. This can be observed from the aerial LSPIV, this kind of PIV. And this is another example of the aerial LSPIV. This is a very heavy damage of the Shinkawa River in the 92,000 disaster. From this, I get the aerial footage, then, and I get the data from the video VH tape, and I have analyzed by developing the image stabilization. So from this, I get the very beautiful velocity distributions like this. This is the levee broken area, and you see here that the broken inundation area, towards the inundation area, the flow is going outside. This can be observed just from the broadcasted videos. And this is another example of the aerial LSPIV. At this time, this is another flood of the Yodo River. The images were taken by manned helicopter, and you see here the surface has some kind of textures, but the flight looks rather fast. But from this, I get the velocity distribution by applying the PIV for each frame, and we get the very beautiful velocity distributions of the tributary of the Uji River, Katsura River, and another case, this is the main flow area. In the Uji, this is the main Yodo River channel. So the maximum velocity was about 3.3 meters per second. So for each set, we get the applied instantaneous PIV and then overlapped the image. This is maybe the first trial of the aerial LSPIV by using helicopter images. Another example for this is just the start of the space-time image velocimetry. You see here, we pay attention to some areas, a kind of striped area, and what I was observing, the striped image has some kind of textures, and we place it in a vertical direction, then I can find some kind of textures moving in a downstream direction like this. And from this, we can get the velocity 1.26 meters per second. But to consider, we can say that this width of 3 meters can be reduced to 1 pixel. So I noticed that by arranging the strip-shaped pattern vertically, we can calculate the speed from the inclination of the pattern. This is the original idea of the space-time image velocimetry. So finally, outline of the STIV is here. Not finally. This is a given original idea to the Shinano River in the middle of Japan. In the STIV, maybe the Mark has already explained in detail about these techniques, but let's take a look at this picture. So in this technique, we set search lines like this. In the ortho-rectified image, the search lines are drawn in this case at the spacing length of 5.46 meters, and it covers the 160 meters of river ridge. And for each search line, we get the space-time image like this. If you enhance the image, we see that striped patterns can be observed for every search lines. For example, if you pay attention to this number 10, somewhere around this, the striped pattern has this inclination, and this is the length is 23 meters, and this is 10 seconds. So actually, from the definition of the velocity, the pattern moving in the downstream direction is 2.3 meters per second. This is the STIV result, 2.29 meters per second, and it's a very good agreement. And but still, there are some skeptical idea if it is really a velocity or not. So we have compiled field research with IIHR, Yodo-san, and we have measured both from image velocimetry and ADCP. This is the first one. Like this. At that time, we used ADCP and STIV, and we measured the velocity distribution in the transverse direction like this, and we applied STIV and LSPIV. And in this case, so we get the ADCP has this kind of profile. This is a missing area. And if you see carefully, the ADCP distribution closest to the water surface velocity distribution, and LSPIV or STIV has in good agreement with each other. And I was confident that the surface texture's movement can be used as an indicator of the surface velocity. So to check the discharge, STIV yields 100 cubic meters per second, LSPIV 98. ADCP is a little smaller than this, but this may be due to the lack of this missing data. And this is another example of the one. Maybe many are worrying about the measurement during the night. So this is maybe the first image that measures the surface, took the picture of the image from during the night. This is actually 8 p.m. during the night, and I use a far infrared camera for river flow. So this was very successful in measuring the surface velocity during the night. And after that, from this, I'd like to talk about STIV algorithms. There are several algorithms we have developed. First one is a deformation method. In this case, we deform this STIV so that the cumulative integration of the pattern would give a certain critical value. And this is the very, very original idea. And the second one is gradient tensor method, which is popular in the KU-STIV software. And we use this kind of equations. I'll skip this one. And the Third one is a Kesta, which my student Notori has originally developed. And with this, we use a log polar transformation of the autocorrelation function, and we get a very beautiful picture of the surface resting. And in applying the applying the surface velocimetry into the surface pattern, we have to be careful about the waves appearing on the water surface. So there are several waves. Some are dispersed wave components, advancing waves, retarding waves, and some are turbulence. And what we have to pay attention is the turbulence component. This is the line here. This is a spectrum of the Fourier transform image of the space-time image. So we have to be careful that we pay only attention to the turbulence component here. So with this idea, I have developed an algorithm, masked Fourier transform. So from this STIV can be improved like this, and from this we can get very easily apply any kind of techniques. And from this we get very easy to handle images can be obtained by this one. And the third one is the deep learning technique, which you have just published. And from this, there are many training of the original. We use actually 36,000 images for training. And from this, we get the very good agreement with the surface patterns. So now it's available on the Hydro-STIV, and maybe Mark can have already explained about it. And another example is the flash flood measurement. This is a very high flow. The velocity goes up to more than 5 meters per second. But even with this, we get the very good velocities. And from this, we get the rating curve only by one flood. Starting from water rise is about 4 meters. And this is a comparison with the KSTV and the Hydro-STIV. This is old version. And after that, we have, starting from just last year, we have moved to the Hydro-STIV. And from this, we have deep learning mode, and drone mode, and real-time measurement mode. And image stabilization mode can also be available, and water level measurement can also be done from within the framework of Hydro-STIV. And another example is the STIV, space-time volume velocimetry. This is a kind of PIV, but it can measure a large area by, in this case, 8 flights can only cover the 900 meters of river reach. I'll skip the detailed explanation, but from this we get a wide range of rivers by taking only 8 shots from the drones. And another one, which is interesting, is this one. This is the image taken by the broadcasted helicopter, and I'll skip the detailed explanation, but you see here the images can be stabilized even when the background shift is very, very distorted. From this we get very beautiful inundating flow like this. So this can be available in the near future in the Hydro-STIV. So this is the overview of my research on STIV again. And starting from PIV for aerial photographs, and the KU-STIV developed, and we have developed Hydro-STIV just recently. So I'd like to give you some future improvements in surface velocimetry. This is a kind of challenging for me and active researchers here and the audience you attending. These are listed on the abstract of the paper. So maybe it's the most important thing is one of the things is reasonable estimation of surface velocity, surface velocity coefficient alpha, and evaluation of wind effect or automatic system measurement by drone or something like this. And some researchers have already done, but the use of photogrammetry for ground controllable GCP-free measurement is also a very useful technique in the near future. Maybe, and finally, the usage of footage from satellite is a rather promising technique to cover the wide area in the world. Thank you for your kind attention, and I'd like to talk to you in the near future in the UK or in the world. Thank you.